everybody here? Not everybody is here. Oh, wait. There we go. All right. So two things for today. How's everybody doing, first of all?
Good.
Yep,
Good.
good.
How's everybody doing?
Yep, good.
Good.
Everybody surviving the pandemic okay?
So far.
Good. So on today's list of things is I want to go through non-parametrics since we didn't get to do that on Monday, and I want to get started and get as far through the two-way analysis of variance as we can. There were 3 screencasts up: the non-parametric screencast, the two-way ANOVA, which was kind of part 1 of the two-way ANOVA, and two-way ANOVA part 2. So let's start with non-parametrics and let me know any questions you might have about that. It's fairly short because there's not a lot to it.
So we would use it kind of as a last resort after the Levine and the Shapiro don't work out. Is that right?
Generally speaking, people employ non-parametric statistics in those cases when you have non-normality or when you have a lack of homogeneity of variances, because those are the two assumptions that you don't have any control over. So for example, you have control over whether you take your data independently of one another. You have control over whether you select your data randomly. You don't have control over how those data turn out. And so when you get lack of normality or a lack of homogeneity of variances, what that means is that you technically don't satisfy all the requirements necessary for doing an ANOVA and being able to trust the outcome of the ANOVA. So you can still do an ANOVA. You can do an ANOVA on any data set that has the structure of an ANOVA. The question is, what is your type 1 error rate as you make a decision about the results of that ANOVA? And give me just a minute. Yeah, I think my non-parametrics stats book is at my house because I've been working from home. But those assumptions that are on slide 4, those are the assumptions for the non-parametric methods. And these are the assumptions for virtually every non-parametric method on the market. And it's the third one that deals with normality and homogeneity of variances. And the assumption is the populations are identical except for a possible difference in location for at least one population. And that's tricky because what that means is that if you're using a non-parametric method because you have a lack of homogeneity of variances, then you still violate the assumptions of a non-parametric test.
Right. Yeah. The word identical is kind of a loaded.
Well, what it means is that you can have a population, and I drew something similar to this. You can have a population that looks like this, where this is population A. You can have population B, but population B has to look exactly like population A, except for location. Let's say that this is the median of the population. So these two populations have similar variance. What they lack is they lack normality. But as a result, you could do a non-parametric method on this and it would work out just fine. On the other hand, if this was population A and population B, these are both non-normal. but they're both non-normal in different ways. And they both have similar variance structure, but the non-normality is one is skewed right and one is skewed left.
Mhm.
In order to justify using a non-parametric method, both of these would both have to be skewed right. In a similar way, and this is the example that I've given to you a number of times in class, you're going to have two normal distributions, one of which has a much greater variance than the other. A non-parametric test is no better at avoiding type 1 errors in this case than a parametric test is. And so that paper by Zimmerman, which I guess I didn't ever, I should upload that. That paper by Zimmerman basically discusses two violations of normality, two violations of parametric tests, the normality assumption and the homogeneity of variances assumption, and says, well, what happens when you violate both of these assumptions? And what happens is non-parametric methods aren't any better than parametric methods. And as a matter of fact, non-parametric methods are generally less powerful because in many cases you're reducing your data down to ranks. And so you lose some information in that way. And actually non-parametric methods generally do a worse job than parametric methods, even when you violate these assumptions pretty badly in some cases. So I forgot to do that between last time and this time. I'm going to just put that up on the Moodle site so everybody has access to it. Other questions?
How do you find the degrees of freedom for the error column or like the error residual?
This is in
Oh,
the
is it when
non-parametric.
we ask two-way ANOVA questions?
I'm sorry, what was this?
Can I
Oh,
ask
in
a
the
question about the two-way ANOVA, or are we just talking about non-parametric?
let's talk about two-way ANOVA. Let's finish non-parametric tests first, and then we'll move on to two-way ANOVA.
Okay, sounds good.
Any other questions about non-parametrics? The Kruskal-Wallis test is simply the non-parametric equivalent of the ANOVA. The Mann-Whitney U-test is the analogous method for a two-sample t-test. And when we get to two-way ANOVAs, the non-parametric equivalent is a thing called the Friedman's test, which you'll see on your daily schedule we'll get to after we've covered two-way ANOVAs thoroughly. Anything else?
So will we need to know how to do a Mann-Whitney U test?
No, I could have taught you that at the time, but it's easy enough to look up in a book, the
Okay.
equation. Essentially, it uses the same ideas that the Kruskal-Wallis test uses. The calculation is just slightly different, but it basically uses these sums of ranks to basically say, so if you have the logic of these tests is that if you have in sample A, values of whatever your response variable is, 56, 57, 69, 72, 84, 70, 86, 92, 105, 110. If you throw these all together without thinking about what sample they come from and rank them, this would be rank 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If you sum this rank, that's 9, 10, 11, 12, 13, 14, 15. If you sum this rank, that's 19, 27, 34. This rank is 40. So the sums of the ranks should tell you something about whether or not the two samples are different. because when you rank them all together and then put them back in their treatments that they came from, if there are no differences, then the sum of the ranks should be similar. And if there are differences, the sums of the ranks should be different. So they're all these methods are based on converting data to ranks and then calculating something about those ranks. So when you see the equation for the Kruskal-Wallis test, which is on slide 6, that big R is the rank. So the big R rather is the sum of the ranks assigned to a particular sample. And so in all cases, it's using these rank sum methods. And the beauty about this is that, especially in biology, Maddie, since you're the one asking this question, oftentimes if you have biological data, the deviation from normality is going to almost always be positive skew. And when you convert these from the actual metrics, the actual numbers that you have, to rank sums, all of these outliers that make up these tails are going to be pulled in. And so rather than differing by maybe hundreds, if you're doing, for example, cell counts or something like that, it's going to be just a difference of 1. And so it removes the effect of those outliers in these positively skewed data sets. The mode is here, the median is somewhere like here, and the mean is way out here. And it's because the mean is particularly sensitive to outliers. And so using means is not the best thing to do when you have non-normal data, when you have this. And so we just use methods that convert things to ranks. Does that make sense?
Yep.
Okay. Other questions? All right. Then let's talk about two-way ANOVA, which was kind of the next thing on our plate. Maddie began with asking about degrees of freedom. If you all go to the Moodle site and download the version of this PowerPoint that is currently on there, I got some questions in the interim since Monday about some difficulties with doing the calculations. Normally, I would write these on the board, and because I haven't fully changed my mind over to doing this remotely, the formulas are not on the board. So I added a slide 5, that actually has formulas from your textbook on how to calculate these things. And so if you open up the PowerPoint for two-way ANOVA with replication, you're going to see I have table 9.8 from your textbook. So if you don't have that PowerPoint, you could also just look at table 9.8, and it actually shows you the calculations. Yeah, what you see here is, let's say that we call source A. Can you guys all see my screen?
Yes.
Yeah.
Okay. So if we call A the rows and B the columns, the way you get the sums of squares for rows is basically the row means minus the grand mean squared multiplied times the number of individuals in each sample times the number of rows that you have. In the same way with column, it's the column means minus the grand mean times the number of observations in each sample and the number of columns. So these are all weighted in the same way that the single factor ANOVA was weighted. It's all weighted by sample size. For the interaction, it's this complicated thing. We hardly ever calculate it that way. What we generally do is we calculate the residual sums of squares and the total sums of squares, and then we basically subtract row sums of squares, column sums of squares, residual sums of squares from total sums of squares, and that gives us the interaction sums of squares. But in response to Maddie's question, the residual degrees of freedom is the number of rows times the number of columns times n minus 1. And so that's where the degrees of freedom comes from. And this is, once again, table 9.8 in your textbook. So if we go to the next slide, which is this really tiny data set, it's pretty easy to get the grand mean. You just add up all of the numbers regardless of treatment and divide by the total number of observations you have. That's basically taking the grand sum, which is right here, and dividing it, in this case, by 12, which will give you 597.75. Then, to calculate the within sample variance, you do it the same way you always have done it. You basically take this value minus its mean and square it, add that to this value minus its mean and square it, this value minus its mean and square it. Can you see me highlighting things
Yeah.
on the screen? Yeah. Then those things summed up should sum to 466.7. Do the same thing for this treatment combination. That should be 6,738. Do it for this section. That should be 3,752. Do it for this section, and that should be 708. All four of these added up is the sum squares within, which is 11,666.67. That plus the sums of squares due to subgroups is the total sums of squares. So the sums of squares due to subgroups is what is the difference between all of the means from the grand mean. So you would take this minus this squared. You would take this mean minus this squared, this mean minus this squared, minus this squared, and this mean minus this squared. They would once again get weighted by the sample size. Let's go back and make sure that I'm saying that correctly. Oh, it's not in here because it's not really a sum of the squares that we normally calculate. It gets weighted by sample size, and that's that. This 65,903 plus 11,666 should equal 77,570.25. So subgroup means plus sum squares within is the total sums of squares. So now all you have to do is do sums of squares rows and sums of squares column. And then once you have that, you know what the total is, you know what the error sums of squares is, or residual sums of squares, you know what the row and column is, and then from that you can calculate what the interaction is. The interaction is the most cumbersome one to calculate. And so what I typically do is I calculate all the others and then subtract to get it.
Hey, Paul, real quick, P
Yeah.
is number of rows and Q.
In this case, it's number of rows and Q is number
Okay.
of columns.
Okay. All right.
Yep.
All right. Sum of
And it doesn't-
squares. Well, sum of squares for rows. I've always taken that sigma of the squared differences and then multiplied only by n, not N Q. I don't know what that Q is.
You should, Q is the number of columns that you're doing it across. So in this case, it always ends up being 6 because it's a 2 by 2 thing, and sample sizes are done. But so here you have 3. So if you're doing the sums of squares for rows, for example, so you're doing this one right here, Q is the number of columns that you have. So in this case, it's a little misleading because it always ends up being 6, but it's 3, which is the sample size within each sample. That's what the little n is. But you're doing this across fresh and rancid fat types, so that's 2 columns.
Wow.
So let's see. This all comes from the Excel file that I have. That is not the Excel file that I want. Let me go and get the Excel file that this actually is. Excel file I was looking for. I'm gonna stop sharing that screen and share another screen with you. So here is can you guys now see an Excel file?
Yeah.
Okay, so for these kinds of things, when I'm making up an example to put on a slide, I will oftentimes go and figure it out in tabular form. So this is the data file that you're currently looking at on your PowerPoint. Oh no, it isn't. Yeah, this is the interaction one. Okay, yeah, this is the one that you're currently looking at. So it should be rancid 592, 538, and 476. So when you go and look at the row cell here, you'll see up here in the formula line, I have 2 times 3 times the sums of the squares. And down here, I actually just simplified that to 6 because it's going to be 6 all the time. And so that's what it's basically doing. So I get these numbers. If you just added up the sums of squares, you would find that this number would be way too small, and it's because you haven't weighted it by the sample sizes, by the number of observations per sample and the number of different treatment levels that you're calculating this across. Does that make sense?
Yeah.
You don't
Where does the 8 error degrees of freedom 8?
Oh, that's just p minus 1 times q minus 1. Oh, error. Sorry, that's
That's the
n times.
residual.
Sorry, that's the residual sums of squares. Oh, and you can't see me because I'm writing on the board. N is the number of observations in each sample. So for this example, that's 3. P is the number of fat types. Q is P is the number of sexes. Q is the number of fat types because P and Q are columns. And so that's 2 times 2 is 4, and 4 times n minus 1, which is 2, 4 times 2 is 8. That's where that comes from. So
Okay.
go back and look at your PowerPoint again. In the residual in the residual column, the error column, P times Q times N minus 1. In this case, it's 2 times 2 times 2, which is
Yeah.
8.
Okay.
Yeah. And your residual will always be a relatively large number compared to your other degrees of freedom, because you hopefully have lots of samples within each, lots of observations within each sample that then gives you the power to do something with. And once again, these should all sum to the total sums of squares, which is just 1 minus your total sample size. So in the ANOVA table here, you have 1 row degree of freedom because you have 2 sexes. You have 1 column degree of freedom because you have 2 fat types. You have 1 row by column interaction, fat type by sex interaction, because it's just the degrees of freedom of row times the degrees of freedom of column. And then you have 8 error degrees of freedom, and that should always equal up to the total degrees of freedom. You have 12 observations total. 12 minus 1 is 11. All right, other questions?
You said that the error was the residual sums of squares times what? In like that last example that you given?
It's just the residual sums of squares. Or are you talking about degrees of freedom?
The error, like what you were showing us in the Excel
Oh.
file.
Yeah, error and residual are the same thing. They're just 2 different words for the same thing.
Oh yeah.
Yeah. And I flip back and forth between them all the time.
And Excel uses the word within, right? Same thing, right?
Yes.
Within.
Yes. So,
Yeah.
yep.
Okay.
So the reason for this is every textbook does this differently. Mean squared within, mean squared error, mean squared residual. All of these are the same thing. And they're the same thing whether it's a mean squared or whether it's a sum squared. It doesn't matter. I tend to use residual or within because they make the most sense to me, because this is within sample variation. And this is residual variation, which has a very specific mathematical meaning. It's the individual values minus the mean squared. So you'll tend to see me saying when I speak it, either mean squared within or mean squared residual or sum squares within or sum squares residual, because they make more sense to me because they actually mean something. In one case, they mean something relative to a sample versus a treatment. And in the other case, it refers to the actual way in which you calculate it. So sorry if that's confusing to you, but it's good to know how different people talk about things, because you pick up any given book and they're going to talk about it in slightly different ways. You'll even see this in our documentation when you go and look at people's, when somebody develops a package, they go through and they define what everything is in the package and how the package works. And you can find these things by just searching for, for example, doing an ANOVA, search AOV, open close parentheses, and it will probably take you to the CRAN site, which will have the package documentation for whoever developed that package. And you're stuck with however that person talks about error sums of squares or residual sums of squares or sum squares within. The nice thing about this is that when you have a good enough facility with the material, give me a minute to get R back up on the screen here. So can you guys now see an R script?
Yeah.
Yep.
This is the R script for the rat fat data. So one of the nice things about using the correct terminology is that when you do things like go to check normality, this section right here, the writer of the package that does both linear models and analysis of variance, they use the term residual. And so if you want residuals, all you have to do is type residual out in front of the model. So this is the model. We're using linear models here rather than AOV. They both do the same thing essentially, but you're using this statistical model where growth is determined by an interaction of fat and sex. But rather than giving me the analysis of variance out of that, I want you to give me the residuals. And when you run that, it just gives you a bunch of residuals, which in this case are unsquared residuals because you have both positive and negative values in this case. Because what we're testing is we're testing normality. So in this case, the residuals that you use for testing normality are not squared. So anyway, that's that. What else? Is that all the questions you have?
Dr. Klawinski,
Yes.
I'm kind of confused in the math part of it. Would you be able or willing to create like a sheet or a PowerPoint or a file, whatever, with all the formulas and step by step how to calculate each one?
So yeah, I already have something done like that. I was going to post it after we had this conversation. So this sheet, well, you can't see because I'm not sharing that sheet anymore. Give me a minute, give me a sec. This sheet that I have here, this thing that is all done,
Yep.
it's actually an Excel file, and when you click on these cells down here in the Excel file, it will show you the equation up top. And that equation should comport with these equations.
Okay. Yeah.
Okay.
I mean, I cannot read that. Like it's super difficult for me.
Okay. You mean you can't see it, or you don't understand it when you see it?
No, I understand when I see it, but I don't see like actual like I of course there's use for it, but I cannot like put it on paper, you know what I mean?
Okay, so this first thing here, which is the sums of squares for rows, go to this data file. What it's asking you is you've calculated the row means, 615.5, 580. You calculate sums of squares among means the same way in a two-way ANOVA that you do for a one-way ANOVA. So if you want the sums of squares for rows, you take 615.5 minus the grand mean, square that guy, square that difference, and store it. Take 580 minus 597, square that difference. That's what the squares are here. It's the row means minus the grand mean squared. You take that sum and then you multiply it times the number of observations, which in this case is 3, and the number of columns that made up those row means, which in this case is 2. So this would be 3 times 2 times whatever the sums of squares are. Same thing with the columns. For doing sums of squares columns, it would be 669.17 minus 597 squared, save that number, 526 minus 597.75 squared, save that number, take that sum of the column squares, multiply it times n, which is once again 3, and the number of rows that went into making up those column means. And so that's the sums of squares times n times p. 3 times 2 times whatever the sums of squares are. So I'm not a big fan of, as you guys know, I'm not a big fan of memorizing equations and using that to help you understand how to do a thing. But when you see an equation, if you know how to do the thing, the equation should then begin to make some sense. So let me get out of this. So I'll put the spreadsheet up that I have built for the rat fat data, and you can look at the cells and see how those things are calculated.
Awesome.
But fundamentally, though, this is an old set of ideas. Do you recall this equation?
Yes, sir.
Yeah. This is the sums of squares among. It's the mean of whichever treatment, the means of the different samples within a treatment minus the grand mean. It doesn't matter if this is among rows or whether this is among columns. It's the same idea. So at the beginning of this, at the beginning of us going through and calculating variances, I really stressed the numerator part of the variance equation because we're going to be revisiting it over and over and over and over again. So it doesn't matter whether it's among treatment levels in a single factor ANOVA or if it's among rows and among columns in a two-way ANOVA, it's the same thing. There's nothing new here.
Okay.
Same thing with sums of squares residual. This was always the sums of squares of each of the individual values minus the grand mean squared. It's exactly the same way in a two-way ANOVA. It's just that you have those individual observations divided up among a bunch of different treatment levels. But what you do is you just ignore all treatment levels, look at the entire data set and say, how does each individual value differ from the grand mean? That's sum squares residual. There's nothing new about the math. The math
Yeah.
is the same math that you've always been doing.
Okay.
Does that help?
Yes. Yeah. And I'm waiting for the Excel file you're gonna post with the math formulas. Yeah.
Yeah. So you have to pay attention to what the actual cells are that are in the Excel files to get what is in the Excel file relating back to those formulas that are in the PowerPoint. But like I said, if you can do a one-way ANOVA, you can do a two-way ANOVA, you can do a four-way ANOVA because the math hasn't actually changed.
Thank you.
Sure. What else? So in this first example, what you should have seen is that the interaction term doesn't affect anything. All that really matters is column, which in this case is fat type. So if you give rats fresh fat, and I don't know why you would do this. Once again, this is an example from a textbook. I don't know why you would give rats fresh and rancid fat, but when you give them rancid fat, they grow less well than when you give them the fresh fat. And that effect is the same whether you're male or a female, ultimately. And so this is what the data look like in terms of graphing it out. And what you can see here is that it looks like you probably have some homogeneity of variances issues, although when you go and test them, you don't find that these variances are different. Why not? You guys are still there, right?
Sorry, can you repeat the question?
Yeah.
So can you guys see the data plot that I have on the
Yes.
screen? So do those variances look like they're similar?
No.
They don't. They don't to me at least. Yet when you do a Levene's test on this data set, you don't find that the variances are different. Why? Anybody? Bueller? I hear nothing but silence. So those variances, so the 95% confidence interval, can you guys still hear me?
Yeah.
Yes.
Okay.
Yeah.
So when you look at female growth under fresh fat, you see that the mean is, I don't know, somewhere around 640, and it goes way up above 700, it goes way down, not quite to 500. And the 95% confidence interval for males is up around 700, but it only goes up somewhat above 700 and ends like at 650. To me, those seem like really different variances. But when you conduct a Levene's test, you actually find that there's no problem with these data. Why? I'm going to share a different screen with you now.
I mean, it's such a doggone small sample size.
It's such a doggone, that's not how I would have phrased it, but yes, it's a really small sample size. So here's a little R script that I've written to analyze the rat fat data. Let me make sure that, can you guys see my script?
Yep.
So here are the means, and the variances, the confidence intervals are huge, 170, 107, 144 versus 37 and 46. When you do this, you find a significant analysis of variance, basically showing that fat has an effect, but sex does not, and the interaction is not there. These are the same numbers that are in the ANOVA table in the PowerPoint. When we go down here and test residuals and do a Shapiro-Wilk test, we find a Shapiro-Wilk statistic and a p-value that shows that they are not different from normal. And when you do a Levene's test, you also find that the variances are not normal, even though when you make a figure of the data, the data look really different in terms of their spread. And the reason for this is that you just don't have enough statistical power to detect that these things really have different variances. And this is the problem with relying on statistical testing for making decisions, is sometimes you basically say that these variances are not different when they actually are. You basically are making a type 2 error, saying that two things are not different when they actually are, because you lack the statistical power to see the difference that is there. So if I were a person who is being asked for advice about this data set, I would say, we conducted a Levene's test and found that your variances were not different, but I wouldn't just proceed blithely with doing an ANOVA and interpreting that ANOVA correctly, because I'm pretty sure that those variances are different. Because I look at the data and I see that the data have widespread in some treatment combinations and narrow spread in other treatment combinations. And regardless of what the Levine's test, if they look different to me, and I know that you only have a sample size of 3, I would say to the researcher, is it possible to go and get some more rats and feed them some more fat? So as you're looking at things like the results of Levine's test, always look at the data and exercise some judgment about those data when you're making decisions on whether or not you meet the assumptions for doing a particular test. Before you go and turn yourself in knots trying to make the data conform to the assumption, ask yourself, well, is this really something that I need to worry about for this particular data set? In this case, the Levine's test is saying, no worries. But I look at the data, I'm like, I'm a little worried. Okay, you guys understand my rationale?
Yes, I think so.
Okay. Too many times people plug numbers into a computer, it spits out an answer for them. They take that answer, they run off and write a paper about it, having not ever really thought critically about what went into the computer giving them that answer. And that is almost always a bad way of going about things. Which is one of the reasons that I encourage you guys to run your scripts line by line, is by running them line by line, you have the opportunity to take time out and say, okay, I just did this thing. Is what are returned to me, what are should be returning to me, what does that mean? How should I respond to that answer? Now, in some cases, you're reading in a data file and the answer is, I read the data file in, it looks like the data file is read incorrectly, and then you just move on with life. But in some cases, like with a Levine's test, you should say, you know, okay, well, what does that Levine's test do? Which is why oftentimes in scripts, you'll see me making graphs shortly after I do something like running a Levine's test, because I want to actually see the data. I'm like, okay, you told me everything is okay. Is everything really okay? So that is that. I'm going to go back to the PowerPoint. So this showed that there was an effect of fat type, but no interaction. So in the second half of this, and this is what the figure looks like. In the second half of this, all I did was I basically took the fat types and I switched them within the males. So now what was rancid is fresh, and what was fresh is now rancid. So I just flipped these two things to basically show you what an interaction would look like as you go and calculate it. The sums of squares subgroup doesn't change. The sums of squares residual doesn't change, or sum squares within doesn't change. But what does change is the column means. So they were 669 and 526. Now they are 589 and 606. This then changes the sums of squares column, and it puts more of the variance in the sums of squares interaction term. See how high this is in this case rather than in this case. So basically we just flip these two. And what this means is that when you then go and calculate an ANOVA, in the second ANOVA, you see that the row by column interaction is now the significant thing. Sex is not significant. Fat type is not significant. It's the interaction that is significant. And so when you get to a graph of the data, the reason that sex and fat type don't have an effect is if you average across fat types within male, this plus this is going to give you something in the middle. Average across fat types within female, that plus that is going to give you something here in the middle. Those two things aren't different from one another. Look at fat type. Within fat type, you see that Male and female are going to give you something in the middle here. Male and female are going to give you something in the middle here. So as a result, the averages across fat type don't change, and the averages across sex don't change. And one of the reasons that those things don't change is that what is significant is the interaction. You feed females fresh fat, they grow really well. You feed males fresh fat, and they grow really poorly. Give males rancid, they do great. Give females rancid, they do poorly. That is the very definition of an interaction. That's why all of the variance that is getting explained in this new way of arranging the data is all found in that interaction term. Now, it doesn't mean that the interaction term will always negate the main effects being significant, but in some cases it might, and this just happens to be one of them because of the particular thing that we did to the data in this case. So that just shows you these are the two ANOVAs, the second ANOVA that we did and the first ANOVA. But once again, the equations are all the same, it's just that the data has been rearranged. Questions?
I have an R question.
Yeah.
When I try to run the Levene's test, it says it could not find the function Levene test.
Okay, that's because you don't have a package loaded.
Oh, okay.
So give me a minute. Let me go to my R. Give me a minute to get there. So before I give you the answer, Grace, go online and search Levene test in your web browser.
Yeah, I did.
What package does it tell you it is in?
That one didn't say a package. Let me look for another.
Are you in R right now?
Yeah.
You can also go to R and in the help tab over here in the lower right hand side of your RStudio script, you can type in Levene test.
Okay.
And it says Levene test, and then it has in parentheses here, it says car.
Or
So what you need to do at the top of your script, you need to always have a little section where you load packages that you think you're going to need. And so this is my R script for analyzing the temperature data. And at the top, you see that I have ggplot because I'm going to need that. RMISC, I'm going to need that. And I need car because I'm going to be running Levene's test.
Okay.
So if you load car, then it will run because that's where Levene's test lives in our land.
Thank you.
Any other questions that people might have about the write-up and the analysis for the temperature data? Okay, does that mean that all your questions are answered? Anybody? You guys are quieter online than you are in class.
Dr. Kowinski.
Yes.
Can I email you later? I just got a lot of tables. I'm very concerned about the report due Friday.
Okay.
Can I email you all my tables because I got a lot of results and I think they're not accurate. I got an F value of 473. I have never seen that before.
Okay. Let me run the data real quick here. That's the nice thing about having computers is we can just run it quickly and load up the temp data. Oh yeah, 473.
Really?
Oh yeah, because they're hugely different. Like they're really different. Like the winter Oklahoma City geckos are 15 degrees centigrade colder on average than the summer geckos. Yeah,
Good.
that's a gargantuan difference.
Yeah, because I kind of cheated the assignment because I ran all the data analysis packages and all the variances and all the stuff on Excel because it's easier for me because I know more Excel. And I saw like huge like differences. And then I ran in R, it's also huge. So I was like, that's interesting. Are we able to plot to put in the final report plots from Excel as well or just R?
I would prefer you do things in R. I'm shocked to find that you ran this entire data set in Excel.
I mean, it took me 2 minutes.
Oh, really?
I mean, yeah, it's easy.
Wait, are you using the analysis package in Excel?
I'm using the descriptive analysis, yes, and F value and all those commands.
Okay, yeah. So you need to start doing things in R, not in Excel. I am assuming that Excel has fixed some things in its analysis packages since the 1990s. But when I was in grad school in the early 90s, Excel oftentimes gave you the wrong answer when you did things like doing an ANOVA in Excel. So I broke myself of depending upon Excel for these things. The only thing that I use Excel for is when I'm trying to work out small examples and I just want to check my arithmetic. But I always do it in ways like I showed you earlier where where I'm actually putting in the equations to calculate the things. No, you should be doing this in R. And one of the things that you have to ask yourself once again, so I get this really gigantic F value with this really, really tiny P value, that's telling me that things are really, really different in my data set. Now, when I look at my data set, do I see that things are really, really different? And they are really, really different. And so you can say, okay, I trust that result. For a couple of reasons. The data show me that that's the result that I should be getting when I visualize them. And two, I know enough about how to script in R that I've written my script correctly and it's giving me the right analysis. The other thing that you can do that I do, am I still sharing? I'm not still sharing, am I? My R script?
Are you in your office?
I am in my office.
Can I swing by in a couple of seconds? I'm in a cage right now.
Yeah, just as long as you stay 6 feet away from me.
Oh, of course.
So, so also use the summary SE. Use the summary SE function to get an idea of what the actual numbers are, so that when you then get a plot, you can say, okay, summer Galveston geckos are 30, summer Oklahoma City geckos are 29.8, winter Galveston is 25, winter Oklahoma City is 15. That then indicates that there's this big gap. So that's a 14-degree gap between summer in Oklahoma City and winter in Oklahoma City. The confidence intervals are really small, 0.5 and 0.7. which means that that's just a little, about 1 and a little over 1 above them, combining above and below the mean. That's a very small 95% confidence interval relative to the large gap between those means. That should signal, oh, well, when I run the ANOVA on this, I'm going to get a really big F statistic because these things are actually really different in terms of differences among the means compared to the amount of variation within the means. Because
Yeah.
remember that wait, where did it go? Having trouble finding this section where I did this. So remember that the F value is the variation accounted for by the treatment divided by the variation that is left over that is not accounted for by treatment. Most of the variation in this data set is due to differences among the treatments. And as a result, you should expect the F value to be really big because it's mean square treatment divided by mean square residual. And that should be exactly what you see over there in the graph, which is
huge.
not a ton of variation around the means, but huge differences among the means.
Yeah, I ran the Levine test, and I have a weird value as well. Let me get here.
Yep. And when I was talking to everybody on Monday, I mentioned that this is once again one of those situations where you want to look at a Levine's test result and express some judgment, because the Levine's test basically says that your variances are not equal.
Yes.
And they are not equal. These are a little bigger. The winter ones are a little bigger than the summer ones, but none of them are hugely different. Once again, go back and look at this table right here. Look at the confidence intervals, 0.3, 0.5, 1.12, 0.77. Those are not very big differences in the confidence intervals, given the amazingly large differences in the means. And so the thing that you have to ask yourself is, am I violating the homogeneity of variances assumption to the point that it's going to give me the wrong answer? That it's going to tell me that things are different when they actually are not. And it's not, because when you look at this figure and you look at the numbers, which treatments are different from which other treatments?
The winter.
The winter treatments are different from one another, and the winter treatments are different from the summer treatments.
Which means that it's impossible to be like related or like non-different, right?
I'm not sure what you mean by that.
I'm saying that the data set, so it's not spread out, but it's like different. I plot some residuals, and it seems like pretty like normal distributed, like the graph.
It's not quite normally distributed. The Shapiro-Wilk test is also significant, so it's not normally distributed. So I'm going to
show you a couple of minutes. Yeah.
Yep. I'm going to show you Tukey's analysis here. So basically, Tukey's analysis says the summer populations are not different from one another, but all the other combinations are different, which is what you already knew by looking at the data. And so in this case, the lack of homogeneity of variances isn't preventing you from making the right decision, reaching the correct conclusion. And one of the reasons that you're able to detect these small differences in variance among the different treatments is the fact that you have huge sample sizes in each of these things. You have 52 observations for summer Galveston, 60 observations for summer Oklahoma City, 30 and 40 for the winter populations. With those kinds of samples, it's really easy to find small differences among variances. So as always, look at the results of the Levine's test and say, okay, I see that the variances are not different, or I see that the variances are different. Is that something that I need to worry about? Look to the data. The differences in the means are huge relative to the variation around those means. if I say these means are different, I'm probably not going to be making a type 1 error. So I'm going to effectively ignore the results of the Levene's test because I have a lot of power for that test, and I look at my data and I don't think it's going to lead me astray.
Okay,
Does that make sense?
makes sense.
Okay. What about the rest of you?
So this is another situation where basically your data is more granular than it's basically necessary for what you're looking at. Am I understanding that
Yeah.
right?
Yeah, so
Okay.
these are actually data that I collected. These are my data. I'm in the process of writing a paper about these data. And I collected a bunch of geckos because the purpose of having the geckos was to race them down racetracks and look at their speed. And for that, I really do need quite a few geckos. But while I was collecting them, I collected body temperatures and wall temperatures and things like this of each gecko that I collected. So to answer the question, are their body temperatures different in different populations at different times of the year? I actually collected way more data than I actually needed in
Gotcha.
order to answer the question, but I wasn't really collecting the data for that purpose. I was collecting the data so that I would have data on each of those lizards. And as a result, I just have a huge number of lizards.
Dr. Glowinski.
Yeah.
Why did you choose to go for like 60 geckos in the summer and then just 40 for winter? Why not
They're-
like equal
they're-
ends?
I collected every gecko that I found, and they're just more active during the summer.
Oh yeah, it makes sense. Yeah.
Yeah, because they die at 10 degrees centigrade.
Ooh.
So in theory, they that's their what we call the critical thermal minimum. All right, that's all the time we have. On Friday, we'll talk about two-way analysis without replication. I'll have a screencast up later on this morning, probably about that. And once again, as always, email me if you have any questions, and stay safe.
All right. Thank you.
All right, see you guys.
Thanks.
See ya.
See you in a sec.
Yep.
Thank you.